Lecture 27 covers section 7.4. At the end of today's lecture, you should be able to identify the difference between machines and frames, as well as analyze machines using our equilibrium equations. Machines, unlike frames and trusses, which are rigid structures, are not only designed to transmit or modify force, but unlike frames and trusses, are meant to move. The shape a machine takes is dependent upon the input force, as well as the resistance to the output force. A machine will transform an input force into a larger output force, creating something called mechanical advantage. The output force should be much greater than the input force into the machine. Although machines do move, we analyze a machine at each snapshot in time. If it is necessary, inertia can be considered as an additional force acting on the system. When we do not consider motion, we will analyze a machine just as we would a frame. We will use our equilibrium equations to determine the required input forces or desired output forces. Let us begin by looking at a set of bolt cutters. If our input force is 300 newtons on each handle, we want to determine the force exerted on the bolt at points H and I. To begin, we'll recognize that if a body is globally in equilibrium, each component comprising the body must also be in local equilibrium. We will start with a handle, and we will apply our equilibrium equations such that we can determine the forces acting on the pins B and E. We will start by summing our forces in the x direction, setting these equal to 0. We see the force Fex is going to be equal to force Fbx. Next, we will apply our summation of forces in the y direction, set this equal to 0. We see the force acting on Fey is going to be counteracted by the force Fby and our input of 300 newtons. Since our handle is not a two-force member, we are able to apply our summation of moments. To do this, we'll pick the simplest point within our system. Taking the sum of moments about point E and setting it equal to 0, we see that Fby acts on a moment arm of 0.1 meters, creating a counterclockwise rotation, while Fbx acts on a moment arm of 0.09 meters, also creating a counterclockwise rotation. This is counteracted by our 300 Newton force that's acting on a moment arm of 0.740 meters, cosine 11 degrees, minus 0.1 meters, that's creating a clockwise rotation. Next, we'll apply our equilibrium equations to the cutter head, and we will recall that we must define the forces acting on pin B on the cutter head, acting the opposite directions as previously defined on our handle. This is shown in the figure to the left. We'll start by applying our summation of forces in the x direction and setting them equal to 0. Here we find Fbx is equal to 0. Next, we'll apply our summation of forces in the y direction and set these equal to 0. Here we have Fhy plus Fby will be equal to Fay. Lastly, we'll apply the summation of moments about point A and set these equal to 0. We see that Fhy acts on a moment arm of 0.09 meters, creating a clockwise rotational tendency, whereas Fby acts on a moment arm of 0.180 meters, creating a counterclockwise rotational tendency. With 6 equations and 6 unknowns, we will use MATLAB symbolics to solve this. First, we'll cast our equilibrium equations about the handle. We'll define our symbols Fbx, Fby, Fex, and Fey. Equation 1 takes the form Fex is equal to Fbx. This was the summation of forces in the x direction. Equation 2, which is the summation of forces in the y direction, takes the form Fey is equal to Fby plus 300, where 300 newtons was our input force. Equation 3 is our summation of moments about point E. Here we have 0.1 times Fby plus 0.09 times Fbx is equal to 0.74 times cosine D11 minus 0.1, and this quantity is multiplied by 300. Next, we'll apply our equilibrium equations about the cutter head. We will define the symbols Fay and Fhy. Equation 4, which is the summation of forces in the x direction, takes the form Fbx is equal to 0. Equation 5, which is the summation of forces in the y direction, takes the form Fhy plus Fby is equal to Fay. Equation 6, which is the summation of moments about point A, takes the form 0.9 times Fhy is equal to 0.18 times Fby. With 6 unknowns and 6 equations, we can solve our system. We'll define our equations vector as equation 1, equation 2, equation 3, equation 4, equation 5, and equation 6. we'll define our variables vector as FAY, FBX, FBY, FEX, FEY, and FHY. Our solution structure will solve our equations for our variables. In doing such, we can print to the screen our cutting force, which is force FHY, as well as the force on our two-force member FAC, and the forces on our pins FBY and FEY. In doing such, we find our cutting force, FHY, to be 3,758 newtons, or approximately 12.5 times greater our input force of 300 newtons. The force on our two-force member, AC, is 5,638 newtons. That on pin B is 1,879 newtons, and that on pin E is 2,179 newtons. Note, due to the symmetry of this machine, we do not have to model the lower cutting head or handle. In example 2, let's consider a dynamic machine. Considering the engine hoist below, we want to determine the force the hydraulic cylinder must apply through its full range of motion, that is, theta will go from 0 to 45 degrees, to lift a 521-pound mass engine. In our diagram below, pin A will be the point of rotation that the arm of the engine hoist will rotate about. As we put a force at point B, as exerted by the hydraulic cylinder, the arm will lift. Our engine weight applied at point C will always act downward, and the force exerted by the hydraulic cylinder at point B will always act upward. To simplify our analysis, we will look at the hoist arm itself, and we will create a functional relation between our equilibrium equations and the angle theta. In the top figure on our right panel, we see the configuration when our arm is at 0 degrees. FBY and our weight are parallel, and we will rotate about point A. In the middle image of the right panel, we will look at our arm when theta is equal to 20 degrees. FBI still acts upward while our weight still acts downward. These two forces are parallel. Lastly, when our arm is tilted at 45 degrees, we once again see FBY and our weight are parallel to one another. For us to resolve this problem, it'd be easiest to take the summation of moments about point A. In doing such, FBY acts on a moment arm of 12 inches cosine theta that is going to create a counterclockwise rotation about point A, whereas our weight is going to act on a moment arm of 63 inches cosine theta, creating a clockwise rotational tendency. We have cosine theta on both sides of our equation, and we find FBY is equal to 0.19 times the weight. That is to say, an engine hoist is a well-designed machine such that we have to apply a constant force no matter the angle to lift this engine.